correction is always a little bit subjective, but I think I was pretty fair. Let me go through a few things that I want to discuss and highlight. So the first, one of the first thing I was asking you is, I think you guys understand this really well. Some of you may not have explicitly written it down properly, but accelerated vibration test, you should know by now that what it relates to is a random vibration test first, okay? And random vibration, which is the only type of test that really reproduce the condition that we see during transportation. And the idea of an accelerated test is you increase the intensity and lower the time period of the testing. Okay, that's the two components that's important to discuss. Regarding the validity of the test, so there was a lot of things you could discuss. You could go and look at correspondence. That was in the paper, Kip's paper, when they relate to ASTM 4169. They go through data from the trucking industry where they look at average speed, average distances from a trip in the continental U.S. and things like this, and they find out the correspondence between the two. So that's one aspect. But the other aspect is also the 5-to-1 ratio of compression that appears to be respected for the validity of the test to be satisfied. So advantages and disadvantages of accelerated testing. Okay, obviously you save time and money. Therefore, that's one thing. That's the main thing here. One thing that was very important. I didn't write it down for each copy because there's a lot of you that missed this, and I'm a little bit lazy, so I put an asterisk. Okay, and sometimes you have -1 or -2 depending on what you're missing. So this asterisk, okay, that's what I'm going to talk about now, okay, relates to the fact that in part C, what it says was make sure to address potential issues associated with an increased intensity level that are characteristic of accelerated testing. So part of that question here, and if you have an asterisk, this is why you lost points, is I really wanted you to discuss what is presented in the paper from SEC, okay? And this is where there's multi-components, but what you notice is actually when you increase the acceleration level, at some point, if you look at the critical component, you have actually less of an output on the critical component as the intensity increases. And what is noticed, okay, he actually has a graph when he shows that when the acceleration level reach values larger than 1g, okay, on the way up, there's no issue because the table pushes the package on the table, but it's on the way down. Some of you mentioned that correctly, is if the table goes down with an acceleration larger than 0.1, you know that for random vibration, the package is not attached to the table. So you're going to have separation between the table and the package. And when it does happen, what's going to happen next is that you're going to have some kind of a chaotic or unpredictable behavior, because when the two reconnect, they can reconnect going the same direction, okay, or they can reconnect at different velocity, but you're most likely going to have an impact, okay? And if you do have impacts because of that increased acceleration, you kind of defeat the purpose because you were not trying to test for impacts, okay? Most likely you could have some separation in a load where you have a very high acceleration up, okay? And then obviously it will slow down. You may have some things that, let's say, if you have all the mass attached together, it might not go up and continue to fly away, like if you have a light package or something like this. But most likely, it's not going to happen. Okay, you're not going to have any. It's not most likely going to happen. It's never going to happen. Okay, so that effect is not representative of a real shipment. So that's if you had an asterisk, it's because you were missing part of this, that when you have acceleration more than 1g, and the table is going downwards, you're going to have separation. When the table reconnect with your package, you're going to have an impact, which is not what the test should be designed to do, okay, and represent. So for part D, I think most of you did really good. I wanted to have some discussion at some point and some change or critique of the protocol. Again, this is a little bit subjective, okay? I did remove some points if what you mentioned was wrong, okay? But usually I don't think I removed that many points. So a few things that I corrected for. Let me read my notes here. So one thing, some of you what they mentioned is that you remember those loggers, okay? Those data loggers, they were put on the truck frame or within the aircraft container because they couldn't bolt anything on the aircraft itself. So some of you mentioned that they should put the data logger on the product itself. That's one thing you cannot do, okay? For different reasons. One of them is that some of these loggers are pretty big, okay? They have a good mass, okay? So if you attach it on the product, you change the behavior of your product, okay? Particularly the critical component. You cannot attach a big data logger on something like this. If your product is relatively heavy, you could attach in the lab like a tiny accelerometer on it, but not like a huge data logger. And the other thing is that the goal of their test here, okay, was to design or to gather data from the environment, okay, to be able to reproduce the environment in the lab, okay, to test different products. So their goal was not to test a specific product. I'm talking here about the Amgen paper from ISTA. So what they want is really to get the input. That means what is the variation or the vibration of the truck bed? And it would have been nice to have the vibration of the aircraft, but they couldn't do it. So what they used is one of the most likely units, containers to be used, an LD3 container, and they put the data logger in there. So both ways that whatever you would put in the truck, okay, will vibrate this way. So you can put a loose package, you can put a pallet, but if you use that input to measure, you're going to be able to reproduce or test for these conditions in the lab. Does it make sense? That becomes really the input. So for the aircraft container, then when they have to test, they don't have to test an aircraft container, they have to test what you put inside the aircraft container. Does it make sense? So that is why typically you couldn't or didn't want to attach the data logger on the product. If you mentioned that you wanted, that would have been nice to have more data logger distributed within the truckload, for example, the front, the back. That was something interesting and good. But probably they use the back, so you're going to have a little bit more of a movement in the back. That's why it's fun to sit in the back of the bus, right? Because, so,
wait,
yeah.
Say that one more time? What?
At the back of the trailer, you may have more movement than in the front because it may tend to bounce more if you have vibration and things like this.
Okay. Did they take that into account into the paper? I forgot.
I don't remember exactly, but I remember if my memory is right, they put it at the axle at the back of the trailer. So that's it. And I know some of you had question about the 2 level, so 80, 20%. I honestly really don't know why a lot of protocol tests with 2 levels rather than just one average. My understanding is they want to make sure that if they just want to see if it were to have a patch of time where you have a little bit more rough vibration, you want maybe to test for this. I'll look into it. I know they had a reference in one standard procedures, but the thing is, some of the reference they use in those things are hard to find. They're not like widespread, so I'm going to look into it. And if I find something, I'll mention that, but it's something that is used quite a lot. Let's see. Okay, so do you guys have any questions or comments on this? Okay, good. So, perfect. By the way, I didn't say Happy Monday, but Happy Monday. It's kind of a not a good way to wake up with a bit of rain. Particularly if you had to leave the house around 7, it was kind of pick up the storm. But yeah, I think it's going to be like this for a while. But we're still lucky because in Canada it's like this, like
all the time
for weeks. Like all a week long of this is not fun. So you kind of forget these things. So okay, as I do most of the time, I want to refresh our memory of what we've done last time was the lab demonstration. Okay, but just a quick thing about damage boundary curve. Okay. This is a simple diagram, and I want to just remind you what's the goal of these things. Okay, if you were to do a damage boundary curve, the goal is to find out or establish the fragility of a product. Okay, that means it's not a packaged product. Okay, it's just a product. Okay, and we're going to use that information when we do cushioning a little bit later. So how do you create these things? Okay. Let me go through here. The first step, okay, is what we showed in the lab is to use half-sign types of impulse. And that means all of these impacts are all these plastic programmers, very short duration. And you try to break your product by increasing the drop height every time, okay? So every impact you're creating, you're increasing the velocity change. That's the step 1 here because you're increasing the drop height and you're increasing the acceleration because you have a pretty much the same time of impact, but you have higher and higher drop velocity change, so therefore you have more acceleration upon impact. So that's the first step. Okay, you have the package that breaks, or the product that breaks, the product that breaks, and then you remember there was on this graph we kind of picked up the point just before you had damage as the limit for the critical velocity change. But we also mentioned that based on standards and different procedures, it is kind of understood that the real critical velocity change is going to be somewhere between where you have failure and the point prior to this. Okay? So the idea for this is also typically you use the same product. Okay? Particularly if you have limited amount of product as means. So you're going to use the same product until you get damage. And that's it. If you can spare more product, what you can do is once you find this point, you can start back, okay, to the prior points and do another test and another test and see if you get different variation. And the reason for this is that you may have the effect of multiple impact that can actually create a failure that will not have happened at this drop height if it was a single impact, if it were a single impact. Does it make sense? If you have multiple impacts before, you may get a failure at, let's say, 50 centimeters high, but if you have a brand new product, it might not fail the first drop at 50 centimeters high. So that's something to think about as well. Once you establish this, what you want to find now is the critical acceleration level. And to do that, you pick a drop height that you know has enough energy to create damage. Okay? That means the standard mentioned to pick a critical velocity change, therefore a drop height that corresponds to a critical velocity change or velocity change that is at least pi over 2 times the critical velocity change or 2 times the critical velocity change. You want to make sure you're on the flat part of that curve. So that means you pick a drop height that is associated with the velocity change that is high enough that's going to allow you to test on the flat part of the damage boundary curve. So once you pick that drop height doesn't change. Okay, so you know that from this drop, the product should break. Okay, if there's no protection. Now what you do for this is then you use the pneumatic cylinders on the shock machine and you put some air in there first, but you make sure that they are not too much pressure, so it's a soft landing. Okay, so you drop it from that fixed drop height, okay, with a low pressure, and you measure the acceleration level. No damage. You increase the pressure in the cylinder, so they're stiffer, right? So the change of velocity is going to happen over a shorter period of time, and you do that until you have damage. Same procedures happen. You establish that this is damage. This is a conservative approach to fix the critical acceleration at the previous point, but you know in a way that the real critical acceleration is somewhere between. Okay? So that's the process, and once you've done that for one orientation, typically in a perfect world, if you do these tests and you have the resources to do them, you should do that in different orientation to see if you get a different fragility in different orientation. If your product is manufactured in such a way that is very unlikely that it's going to fall on a different orientation, then you can basically rationally argue against testing multiple orientations. Yes.
So you have to do them for different orientations, but do you have a different damage boundary curve for each of the critical components in the product, or would you just do it for the product as a whole?
You do it as a product as a whole. Okay, so what we mentioned as well is that depending if you test for the critical acceleration or the critical velocity change, the impacts are different. So you may have different failures or different components that will break. What you're testing is if it breaks or part of it breaks. Does it make sense?
Is it typically cosmetic, or does it have to be something critical
that is something you need to identify as when you begin the test. So if you look to the standards, usually these standards, it's kind of really based in a way on the scientific approach. So in the scientific approach, you need to state your assumption or hypothesis, right? So in this, you have to state what you consider as failure. It can be cosmetic, okay? It can be other things. But once it's set, you need to be able to, this is in stone. So this should not be changed when you do these testing after that. So whatever result you have, that's where sometimes it's hard, but if your team established as this is a failure, and you do this and you have a failure at this point, this is the fragility, and that's what it is. Does that make sense? Mm-hmm. Very good question. So this is what we've done. After that, any other question on this? Okay. And for the exam, a little bit like the little quiz, you should be able to draw these things and know where you have damage and not, and explain in your own words how you create those damage boundary curves. Okay, you should be able to do this. So cushioning, we started talking about this last time. We talked about working length, which we've done before. We also forgot again to show you the loose fill. So I'll try to bring some on Wednesday. I need to do something to remind myself. Let's see. I need that. Sorry, I'm just putting that binder here so I'll remember to do something. So we talked about different types of cushioning material, loose fill and dunnage. Okay. We talked about it can be peanuts and stuff like this. We also mentioned that we see a lot of those airbags these days. Okay. So we showed example. Okay. We mentioned that corrugate. It's actually a pretty interesting material to do that because obviously when you think about corrugate, there's nothing, I would say, so exotic or fancy or really, I would say, that will wow you first because we see it every day, but it's a pretty unique material. And depending on how you use it or orientation, you can create things with a lot of different properties. So it's a really useful material for cushioning purposes. We talked about, I think that's how we finish, about newer types of material. We talked about mushroom packaging, okay? That is basically, they grow a mycelium on a substrate that is biodegradable. And they grow it in a mold, so to create a package, okay? That can be then just tossed in your compost at home or whatever, how you, I don't know, some of you may not. Those of you work in or stay in an apartment complex, do they have compost bins now? No. Okay. Yeah, at some point it may happen, but it does make a big difference. I don't know if any of you done that at your parents' place or something, but maybe two years ago we just started to have compost most at house, and I think that the amount of trash we take out, sometimes it's just one bag of trash a week. Okay, it's amazing of a difference it makes. Obviously,
Is that like food or something? Compost?
yeah. Usually, it's you don't want to put meat in there. Okay, but biological waste. So, vegetables that for any reason you didn't eat, or onion skins and whatever leftovers you have that are egg shells and paper. Some you put some paper in there and things like this. So, yeah, it does reduce your amount of waste quite a lot, and your trash doesn't smell as bad as well, obviously. So some company are using this mushroom packaging, and there's more and more, I would say, movement to go away from some of the traditional cushioning material like styrofoam, okay? And I think I showed you when we did the vibration, for example. So styrofoam is used as cushioning material for impact. It's also used for insulation purposes, okay? A different material. But you see more and more, like, for example, recycled shredded cotton. I showed you, right? Some of you at least in the lab. We had like Hello Fresh packages in there. They had like shredded jeans, okay? So these act for insulation, but they also those type of material can be beneficial as well for cushioning. It obviously depends on the weight and the characteristic of your product inside, but these work. These can work. We can have also wood-based material that can be used for these things, okay? That can be like shredded wood, okay? But one of the issues that people don't like to deal with some of these more biological-based materials is that, particularly pharmaceutical companies, that I've heard many times, is that they are afraid that sometimes, justifiably, that bugs and animals are going to be attracted to these. It can be rodents or whatever, but they like to nest in those things, okay? Particularly if you have to have long storage periods. So there's some reluctance in some field to go this way, but as a whole, I would say the industry is going more and more towards trying to be more sustainable, okay? Because more and more customer, okay, wants to go this way as well, and willing to pay sometimes for a little bit more to get at least to get there. So, okay, going to cushion design, and how do we pick a material and the area and the size and the thickness? So we need to have some tools to help us in this endeavor, if you want. So the first thing, okay, is that performance of cushioning materials are often presented using graphical representation known as cushion curves, okay? And again, this is not all material. It depends, okay? You have some material. I think back in the day, Dow Chemical had a big packaging division. I think now it was sold to Sealed Air. But Sealed Air now has a lot of material where you can find cushion curves. Partially, the company sells that material really for cushioning purposes and packaging. So what you have is that for a given thickness, okay, there are curves available for various materials that will relate the static loading with the peak shock acceleration, okay? And you will see that each graph is for a given drop height, okay? So a few new terms here: static loading, and I think that's the only one here that is new. So what is static loading? Okay, we refer to it as SL in here. Is defined as the ratio of the product weight. Okay, that means mass times gravitational acceleration, mg, dividing by the bearing area of the cushion. Okay, so that means. So I don't know if you guys might see, but I'm going to try to draw big. Let's say this is the bottom surface of your product. Okay. So if your cushioning material is like two inserts and cover only these two regions of your product, that area is going to be only the area where the cushion is in contact with the surface. Does it make sense? That's very important. And obviously this can be various types of area depending on the design you have for this. By the way, look at this. The sun is peeking out. Okay, good. Okay, makes me happy. So that is the static loading. Don't confuse it with static deflection. Okay, static loading. The static loading, therefore, has units of pressure. Okay, so because it's a force over an area, so a lot of the cushion curves that are produced use PSI. In the class, and a lot of times, I like to use Pascal, so I'll give you that basically conversion, okay, between PSI and Pascal. And if you need it on the exam, it's going to be provided, so don't worry about this, okay? It is given. So these cushion curves, they look like this. And if you want, on the handout I passed out to you today, you have other examples of these, okay? A bit older version, but the same thing. So this is for a sealed air material. This is called Celuplank 220. I think it was used to be called Ethafoam, okay? But I call it Celuplank now. And what you see here, okay, is the first thing in all of these graphs are for a 12-inch drop height. And then you have first drop, second drop, third drop, and an average, okay, of 2 to 5 drops. And on each of these graphs, what you have is on the x-axis, you have the static loading, which we just defined. And on the y-axis, you have the peak acceleration, maximum acceleration. And on each of these graphs, you have multiple curves. And each of these curves corresponds to a different thickness of your cushion. Okay? So, what we want to find, if you think about this, we want to find how thick of a material we need. Okay? Because the thickness is going to be important depending on the working length. Remember, if you have a certain amount of energy in your cushion, you have an impact, your product is going to deflect the cushion by a certain amount, which you don't want necessarily. We're going to see about this. Okay? You have to take into consideration the working length of your cushion when you do that. So you want to define the thickness and also the area you need to give the protection required. So on these, you're going to typically do or look at if you have a single drop or if you want to protect for a single drop or for multiple impacts, which will be those two guys here. And they change because obviously once you have an impact on a cushioning material, it's going to be deformed, okay? Some of these materials have the ability to go back, but it depends, right? Because some of these foam, for example, if they're plastic-based foam, you can have closed cell foams or open cell foam, okay? Closed cell foam is basically the gas is going to be trapped into bubbles, okay, into the material. So if you have a large impact on these, those bubbles can basically burst, right? And they may not recover their own, the material as a whole may not recover fully what it was before. Does it make sense? Same thing if you have a paper-based cushion, okay? It's not going to recover everything after it's been deformed. If you have open cell type of foam, then the compression or the cushioning is due to, in a way, to viscous flow of air through those channels in the material. So it can sometimes recover fully, sometimes it depends, okay? It may not recover fully. So let me ask you this. What other types of parameter do you think can have an influence on these cushion curves? environmental types of material.
How hot it is.
Good. Temperature. Very good. Okay. So, particularly if you're dealing with plastic base or polymer base, okay, if it's really hot, you can have the plastic that's going to soften quite a lot compared to if it's minus 20 Celsius. Okay. So that's something to consider as well. So, how to create a cushion curves, that's going to lead us or give us an idea of how these things are created and what they mean, okay? So, you need to select a cushion thickness and a drop height, okay? And what you have, okay, is you have to build a device. Just picture if you want a, so you can have guides, okay, like this, and then you affix to these guides, okay, a plate, okay, or platen, where you can add different types of weights, and on this guy you have an accelerometer, okay, and this thing you're going to be able to adjust, okay, and drop it, okay, on a certain material, cushioning material, okay? So what you do, okay, is you adjust the drop height, and you can also put some mass in here, okay, and change the mass, and drop it from different height, and measure the acceleration when you have the impact. So what you do, okay, is you fix, let's say you're working at 12 inch. You're going to start 12 inch, you're going to put a certain amount of mass, and you're going to drop it, okay? And through the procedures, there's just certain time that you have to wait, okay, before the second impact, and you're going to drop it again, measure the acceleration, and so on, okay? Between each drop, okay, you're going to increase the mass, okay? So, let's see. Since cushion perform best on the first impact, usually the cushion associated with the result associated with the first impact are going to be presented independently, okay? And you're going to have an average as you go. So, at this point, you should know what's going to happen. So, if you start with, let's say, an empty platen and you drop it, and then you increase the mass, what's going to be the difference, okay, between each of these drops? What's going to change?
Acceleration.
Why?
The mass.
Why?
Displacement of the cushion.
Very good. Okay, so remember when we looked at the maximum acceleration for shocks with a cushion, okay, as we increase the mass, upon impact you had more deformation. So therefore, the change of velocity happened over a longer period of time. So typically, as you progress, okay, as you increase the mass, you're going to have more, you're going to have less and less acceleration, okay, as you increase the static loading, if you want, because the cushion deflects more and more and more, okay? So you're going to do that, but at some point, okay, what's going to happen is it's going to bottom out. It's going to start to bottom out. So you're going to reach a minimum acceleration, okay? This is where you reach the point where your deflection upon impact is equal to the working length of the cushion. Past this, it's going to start to bottom out. So the acceleration is going to go back up. So in here, in the zone 1, okay, is you have the cushion is relatively stiff with respect to the mass upon impact, or the energy. So it does not deflect much upon impact, okay? As you increase, okay, you get more and more deflection, and the acceleration is progressively going down. So in here, this is the region of lowest acceleration or optimal loading, okay? And past this point, actually it says zone 3, but past here, okay, what starts to happen is that your cushion is bottoming out. And when you drop more and more higher, not more and more higher, sorry. If you drop from higher and higher point, okay, you're going to get higher and higher acceleration because the cushion deflects all the way down and you hit the hard surface, okay, and you get this. So, that's how those cushion curves are established, okay? Yes.
At the slope of 0, that's when it starts to bottom out.
Yes. So, how do we do this? How do we use this, okay? For a given material in a drop height, you need first to identify the peak acceleration level, which corresponds to the product fragility or critical acceleration you obtain from a damaged boundary curve. Okay? So you need to know your product. That was one of the first things we discussed this semester. Know your product, know the environment. So if you know your product, you should know its fragility, meaning what is the acceleration level that you cannot go higher than this, otherwise you're going to get damaged. So you see, it's pretty easy to use these. So once you know this, let's say here was 30 Gs. So you take your ruler. Okay, if you want to have a nice line, I would recommend to use a ruler. Trace a line there. Okay, so that means, okay, everything above that line, okay, does not provide enough protection. Okay, if you do 1-inch cushion, all the acceleration you can get is all going to be above 30 Gs. Same things for 2, same things for 3. 4, okay, is the first thickness where there's a region where you have enough protection. So now you have to select the smallest thickness that will provide sufficient impact protection. So in this case, 5 can do the job, but 4 doesn't. So why use 5, right? We're going to use 4 inches. And that's something to consider as well, okay? Because think about this. Usually as well, in many cases, you will need protection in many dimensions. So having 1 additional inch of cushion, okay, in each dimension, that means you add 2 inches of your box in each orientation. That's a big change of volume, okay? It's a lot of material, particularly if you ship thousands of these things, okay? It's significant. So you need to pick the thinnest possible that will give you the protection. Then, okay, obviously, this will be the optimum protection. This one would be the most cost-effective. Can anyone tell me why?
Because it's the minimum to protect it, right?
The minimum what?
The highest
Thickness?
mass inside, you put the largest mass inside.
Okay, close to this. But let's flip this thought around. For designing the cushion curve, we change the mass, right? Okay? For these, what we have to deal with is a fixed mass. Okay? So the product's mass is not changing. Okay? So you can change something else. Okay? Because the x-axis is the static loading, right?
Isn't that the thickness?
The thickness is already decided. It's 4.
Mm-hmm.
Okay? So that we pick. So now, this point and this point have exactly the same acceleration, right?
Mm-hmm.
So this is 30 G. I can have this point, or I can have this point. They correspond to 2 different static loading, okay? So,
The area?
the area, very good, okay? So, your mass of your product, in this case, is fixed, okay? When you design the cushion curve, you change the mass. Now you're dealing with a fixed mass, let's say 15 kilograms, okay? Now, in here, you have a larger static loading. Static loading is mass, gravitational acceleration, area of the cushion. So if this is fixed, okay, that means you can change that. So if the static loading is larger, that means this is smaller, right? So, in a way, if you go with this choice, that means you're going to have less cushion area, which is good because you save material. You have a more cost-effective. But you know, in a way, you achieve that protection with some bottoming out. But it's okay because it doesn't, in a way, change too much. You still have the same acceleration, but going on this side, you use smaller and smaller area. And going from let's say 0.6, okay, to 1.6 or 1.7, it's a huge change in area, okay, and therefore a huge change of material. So that means how we use those cushion curves, they're relatively simple, okay? You need to know the fragility of your product. Once you know this, that means the critical acceleration level. You draw a line on the damage on the cushion curve that corresponds to the drop height you need to protect against. Boom. You find the thickness that is the smallest that basically crosses that line. Then that would be the recommended approach to avoid over-packaging. You pick the intersection of your critical acceleration with the cushion curve of that selected thickness that will give you the largest static loading. That's because you're going to be able to find for this value the area of your cushion. And it's going to be the smallest area or the most cost effective. Does it make sense? Good. So a lot of things this morning. I'm going to stop here. Okay. So thanks again for coming this morning, and I will see you Wednesday.